Every time you flip a switch or charge your phone, you're tapping into this hidden world of absolutely colossal engineering. Today, we're going to pull back the curtain on the gigantic factories that are literally forging the arteries of our power grid. Let's get into it.
Okay, let me just start with a number for you. 185 meters. That's how tall a factory needs to be just to make a single high-voltage cable. We're talking taller than a lot of skyscrapers, all for a purpose that is almost completely invisible in our daily lives. So right away, that begs the big question, the one we're going to answer today. Why on earth would you need to build a factory that tall? Well, the answer lies in a massive battle against one of the most fundamental forces of nature.
And that force? Yep, it's gravity. It is the single biggest enemy when you're making the cables that power our world. And to beat it, you need to engineer on a truly monumental scale. Here's the deal. A high-voltage cable is basically a super heavy metal wire that gets wrapped in this thick layer of molten plastic insulation. Now, while that plastic is still hot and gooey, gravity is just relentlessly pulling it down, causing it to sag. And even a microscopic thin spot, that's a weak point. And a weak point can lead to a catastrophic failure for the whole power grid.
This all comes down to a really key concept called dielectric integrity. All that means is the insulation's ability to handle incredible electrical stress without failing. And for these cables, it has to be perfect. Absolutely 100% perfect. There's literally zero room for error.
So if you need absolute perfection, how in the world do you get it? Well, engineers found the answer in a very special material, by turning a basic, everyday plastic into a kind of super polymer.
The process is called cross-linking. You start with a common plastic, you heat it way up with a peroxide, and this incredible chemical chain reaction kicks off. The peroxide creates bonds that link all the individual plastic chains together. The best way to think about it is like this. Imagine turning trillions of loose strands of spaghetti into a single, incredibly strong, interconnected net. That net, that's cross-linked polyethylene, or XLPE.
But, and this is a big but, there's a really dangerous side effect here. This whole reaction releases gas, including methane. And if that gas forms even the tiniest little bubble, what they call a microvoid, inside that insulation, the dielectric integrity is gone. The cable is completely useless.
So the solution is to stop those bubbles from ever even thinking about forming. And how do you do that? With immense pressure. The entire curing process happens inside a long tube that's flooded with nitrogen gas at 10 bar of pressure. That's 10 times the normal pressure you're feeling right now, and it's enough to keep that methane totally dissolved inside the plastic. The result is a perfectly solid void-free cable.
Okay, so now we know what we need, this perfect XLP insulation, and we know how to do it, with extreme heat and pressure. That brings us to the two competing philosophies for how you actually build a machine to do this. Catenary Continuous Vulcanization, CCV for short, versus Vertical Continuous Vulcanization, or VCV.
These two approaches could not be more different. CCV lines are these long, horizontal giants. They very cleverly outsmart gravity. They use a gentle curve, a catenary, and they're always rotating the cable so any sag gets distributed evenly. VCV lines, on the other hand, just overpower gravity. They build that massive tower and let the cable drop in a perfect vertical line, so gravity is pulling straight down and can't cause any sag at all.
Now, because it's way more versatile and, frankly, cheaper to build, the CCV method has become the undisputed workhorse of the industry. It accounts for something like 90% of all high-voltage cable production. That giant VCV tower is the ultimate solution, for sure, but it's only really used for the absolute thickest and heaviest cables on the planet.
So let's take a little trip. We're going to follow a cable on its journey, tracing its path from just raw metal and little plastic pellets to a finished, flawless core that's ready to carry our power.
The whole thing really flows through 4 key stages. First, the metal conductor itself gets preheated. Then comes the most important step of all, triple co-extrusion. After that, it gets cured under all that pressure in the vulcanization tube. That's where the chemical reaction happens. And finally, it gets very, very carefully cooled down. Okay, you have to appreciate this, because this is the heart of the entire operation. In just a fraction of a second, 3 separate machines apply 3 layers of polymer at the exact same instant. Because they're all applied when they're molten, the layers literally fuse together on a molecular level. What you get is a perfectly smooth, perfectly bonded system with no gaps, no voids, which is exactly what you need to handle that extreme voltage.
So after that magic moment, the cable enters the long curing tube. The first half is the curing zone, this superheated chamber filled with that 10-bar nitrogen gas that kicks off the cross-linking reaction. The second half is the cooling zone. Here, pressurized water flows upwards, against the cable coming down. This counterflow creates a really gentle temperature change, which is crucial to prevent stress fractures as the new XLP hardens up.
Now, with a process this insanely complex, you might be wondering, how do they guarantee perfection every single time? Well, the answer is the quality isn't something they check at the end, it's built into every single nanosecond of the entire process.
This quote from the research really just says it all, doesn't it? The whole system is designed around constant, real-time quality control. It's not about finding mistakes, it's about making it impossible for them to happen in the first place.
And this right here is the brain of the whole operation. As the finished table comes out, an X-ray system, a kind of all-seeing eye, scans it constantly. It's measuring the thickness and the roundness of all 3 layers with micrometer accuracy. All that data gets fed to an AI control system that makes instantaneous little micro adjustments to the line, making sure every single meter of that cable is mathematically perfect.
So there you have it. From a simple fight against gravity, you get this incredible symphony of chemistry, pressure, and artificial intelligence. These colossal machines are the hidden titans that make our modern world possible. But, as we demand more and more power, for our data centers, our electric cars, all of our renewable energy, it does leave you with one final thought. What new engineering marvels will these industrial giants have to invent next?
Follow my channel for more such videos. Learn tech with SR Barik.